thing you did not mention actually is that everything depends on this matrix to be sparse. If it's not sparse, efficiency. Well, practical terms, right? It won't work if it's not sparse.
I did say sparse at some point.
Yeah, let me get to that point. But since the elements are exponential function, the elements are never zero, right? So in practice, you need a threshold somewhere to make it sparse, right? So can you say something about sensitivity to that threshold, and in particular, how you work with that threshold in your experiments?
Yes. So basically, in practice, you use thresholds, but you use very loose thresholds. So, for example, you don't allow pairwise scores to be non-zero if the deformation on distances is larger than a ratio of 2 or 3. So if you don't have, let's say you expect a scale change of 50% or even 200%. So you have an object like this, you want to match it double its size. If you put a threshold 3, you include all the good ones, you remove most of the bad ones. So loose thresholds, even very loose thresholds, specify this matrix a lot.
So the threshold is not then, no, but that's interesting actually, because the threshold then is not on the score, on the contour.
It's on the individual deformation.
It's on some individual deformation.
Because that's how you actually can build it faster. So let's say you want to, this D has 10 elements, vector D. One is looking at distance, one is looking at angle, one is looking at this and that, and the last one is looking at something very, very complex that you try to. So when you build this matrix, because you still have to visit every element for each edge. So let's say it's fully connected graph. You go and then you choose the way you check these elements in the way of in the increasing order of their computational complexity. So you go the first one, let's say it's the easy one, looking at distance. Fuck, if it's above a threshold, you quit. If it passes the first test, it goes to the second test, it's above the threshold, you quit. So you do not have to compute the whole D to decide that you want to put a 0 or not, which improves the speed, like it speeds up the algorithm.
But beyond that implementation issue, which is important.
But on the elements, yes.
But there's another thing that you should probably mention in the document. It's important because otherwise, if you were thresholding the elements of the matrix, there would be a problem during the learning, because the scale of those e to the minus wd are going to change depending on that. Especially even in IPFP, especially when you start with a uniform level, right? Yeah. So you would not know where to threshold because the level varies. So the fact, no, that was the right answer. The fact that you threshold on something that's independent of that is actually very good.
Yeah, that's. I didn't think of it that way, but yeah. But anyway, I think even if you threshold for very low scores like 0.00 something, you would be fine. But
in the experiment,
no, but M can get scaled arbitrarily.
I'm sorry?
M can take any arbitrary scaling, right, and still give you the same answer. So you couldn't just pick an arbitrary.
Right.
You cannot get a scaling because it's an exponential function that goes maximum to 1. So it's basically you only play with the derivatives of this function. You do not play with the scaling.
So even though the solution doesn't change by changing the scale.
I think you'll be still fine. I think you'll be still fine. But yes, it's probably better to do it this way.
In your experiments, you kept the same threshold across all experiments?
In fact, for learning, yes, of course. It's I can tell you the threshold.
So I think it's just a point of detail, but I think you should mention that in the document. Thinking about it now, I don't think that's mentioned explicitly enough in the document. How this particular detail was. Because how is this particular detail, that threshold was handled? So from your answers, it was handled the right way, but you have to explain that in the document.
I used this card somewhere in the deep, but
I actually learned those thresholds a long time ago when I was designing these scores in a different way. I was learning these scores in an independent way. So I looked at histograms and I took everything that's 99 percentile.
Yeah, you don't even have to explain that. The important point is that the threshold is not on the direct contact of the matrix, number one. And number two, that the threshold is the same in all the experiments. Because otherwise, one could do some really funny things if one went to change the threshold dynamically between experiments.
Oh yes,
so
and you can actually,
you
can actually, some experiments I did not use thresholds at all because I think thresholds is a little bit of, not really cheating, but thresholds encourage, by definition, the correct assignments. So you'll have a difference. In some cases, I tried all possible ways and it works. But
well, so anyway, we can discuss
thresholds
that.
are.
So now for the metaphysical question, which I know you've been pondering, including even last night, which is the following: that so you're not an optimization expert.
Yes. I'm not. Yes. No.
I'm not either. Optimization expert. So what makes you believe that IPFP and all the other things that you presented are better than what people have been looking at in optimization?
Yes. So we had the discussion before. So.
Well, hopefully you reflected on those discussions.
So my answer to that is the following. Most people in optimization, there are several answers that I can give. So most people in optimization look for global optimum, and they look at special cases of the problem where they can find the global optimum, or they look at bounds with respect to global optimum. IPFP does not do that. So IPFP is low. So we do not want to solve the big problem. We just want to solve something that works, and it's low. Also, most problems in optimization are more general. There are a lot of algorithms that work for any constraints, linear constraints, or whatever. So they find very good solutions that are so general, they can work in so many cases. But in this case, if you apply those solutions, they will take longer. They will not be efficient. So IPFP is good for a few cases like one-to-one mapping, many-to-one. I have not thought of other problems. But for what we are interested in, it's a good algorithm, it's efficient, and it's only for these problems of one-to-one, many-to-one, and it's not global. It doesn't claim to have global properties. So I think that's what I've learned after looking a lot of optimization papers and stuff like that. So they have a lot of algorithms. For example, there are so many algorithms based on genetic search. Now, nothing based on genetic search would be good for us because it would be so to take forever, or simulated annealing, or because they saw this NP hard problem as something really, really difficult to solve. So let's apply simulated annealing, let's apply genetic search, evolutionary algorithm, time to search, all this. We don't have time to do that. We want something that is fast and efficient. So maybe we are lucky that we are considering only this problem of matching, and we found something good for matching. So it's not, I don't know how it stands against these algorithms on serious just optimization like the ones they're doing in economy or other things. So this is for matching, for computer vision. Here is doing very well. So that's the comparisons we made are only for computer vision. We do not know. Maybe it will be doing good, maybe well, maybe not. So it's not what we want to do. It's not our job to solve economics problems.
Any other questions from the colleague?
No, I guess I just have one comment, which is there's so much in the thesis that I guess one task is to just select, the sort of key messages and contributions to summarize it. So another really difficult question would be, what do you see as the sort of key contributions? Is it the basic spectral matching algorithm, or is it some of the ways of applying it to these particular problems?
I think at the core of the thesis is this idea of accidental alignments, which is also in your thesis. So
that's one way to answer the question.
So this is at the core. Now, of course, from there, all these algorithms grew. Spectral matching, which is an efficient way of doing it. Then IPFP, which doesn't look like it's using any of those ideas, but at least in the formulation that has a projection, to me it looks very similar. It's just a different beam. It's a projection instead of the unit sphere. And that's how I got the idea of it was just, for me, an intuitive way of going from continuous constraints to binary constraints. So again, spectral matching and again, accidental alignments are guilty. Because of them, I ended up with IPFP also. Now, of course, unsupervised learning, I think, also is possible because of that. Because in math problems, again, that would not work. Because you don't have accidental alignments. You don't have that idea there. It's more difficult in practice. Even though the formulation may be easier than mathematical formulation, but in practice it's more difficult the problem to learn for learning. So I think at the core of it is the problems that arise in matching, geometry, stuff like that have something unique to them. And I think that's the contribution that I kind of spotted that, understood that, and I came up with these algorithms that are based on that idea for solving it efficiently and for learning. So I think this is the main contribution of the thesis, not necessarily applications on recognition, or these are applications, but I think more important as a contribution. And it's more the theoretical understanding of the statistics of this matrix M and algorithms for learning and for solving.